Today we're going to spend a little bit of time at the beginning just working a few problems relating to retrosynthesis with alkylation of the acetoacetic ester. What we do here will apply directly to if you wanted to use the malonic ester. And I'm taking some problems straight out of your book, and hopefully this will give you a chance to see kind of what you need to be able to do. So one of the ways you can write problems that require you to think about synthesis and think about it in a retro sense is to give you a product. This one happens to be a pain reliever, an anti-inflammatory agent called nebumetone. I don't know why it's called that. Maybe they like the home planet of Padme Amidala and Palpatine, but nebumetone. Anyway, whatever. Lame. They say make this via the acetoacetic ester synthesis, or rather make this via an alkylation reaction using ethyl acetoacetate as a starting material. And what I've shown you here, this beta keto ester, is ethyl acetoacetate. So the best way to approach this problem is to look for the structural pattern that I told you about, and that is that products of the acetoacetic ester synthesis are alpha alkylated methyl ketones. So we're going to look for the methyl ketone. You're going to look for the alpha carbon that is not the methyl group. That's this one. And then the bond between the alpha and the beta carbons is the bond that you made in the alkylation step. Everything on the other side of that bond is what was there attached to the leaving group prior to the alkylation step. So the alkyl halide that we would have needed to use would have been this one. Oh, I'm sorry, for the actual pain reliever, there would have needed to be a methoxy group there on the ring. For our purposes, we can just sort of ignore everything other than we know that it needs to be there in the alkyl halide that we're using in the alkylation step. So here's what will become the beta carbon, and it needs to be attached to a leaving group. Let's let it be Br. Okay? So then, if you want to look at how this works in the forward direction, remember that these three carbons, the alpha carbon, the carbonyl carbon, and the methyl group, in the product are these three carbons in the starting material. And the blue alpha carbon on the left is this, oops, that's an eraser, is this alpha carbon on the right. So to do this reaction in the forward sense, we would use sodium ethoxide to deprotonate the alpha carbon to generate the resonance stabilized enolate. And then we would use, in the second step, this alkyl halide in an SN2 reaction, making the new bond between the blue alpha carbon and what will become the blue beta carbon. At that stage, what we have is this. Here in red is our new bond. That's the alpha carbon, that's the beta carbon that used to be attached to the leaving group. And then here is the rest of the molecule. Then getting to our desired product is a matter of doing that decarboxylation, or rather ester hydrolysis, decarboxylation, and tautomerization that we went through in detail last time, where we use water and acid and heat to first hydrolyze the ester, promote the decarboxylation of the beta keto acid, and then tautomerize from the enol to the ketone. Okay, questions about that? Do a couple more. Let's do another example. Okay, here is a molecule that you can also have made via the acetoacetic ester synthesis. Again, your first task is to identify the methyl ketone, because that will then tell you what bonds you had to make in this process. Here is the methyl ketone. Then you find the alpha carbon that is not the methyl ketone, and you find what it's bonded to. In this case, it's bonded to two things, two alkyl groups. We would call this alpha-alpha dialkylated. And alpha-alpha dialkylated methyl ketones you can also make from the acetoacetic ester starting material, but you're going to have to install two different alkyl groups. And we've done that before last time. Here are the two groups that you would have to install. One has, let's see, the pink beta carbon, and then the other has the green beta carbon. So the alkyl halides that I would use would be, again, everything from the pink beta carbon on, those atoms, and then a leaving group attached to the pink beta carbon. And then I'll do the same thing over here for the green alkyl group that got installed, everything from the green beta carbon over plus a leaving group. And presumably you would do this reaction in the following way. You would use sodium ethoxide, then one of these, and I'm choosing one of them first. It likely does not matter the order that you put the alkyl groups on. So here's the new bond that you would have made with the pink beta carbon. At this stage, we still have one alpha proton on the blue alpha carbon left. So you can do another alkylation step, sodium ethoxide, and this time the other to make the enolate, and then the other molecule, the other green alkyl halide. And at that stage, I will have made the following, let's see, no, we don't want that one to be red. So here's the pink alkyl group. And then the green alkyl group, which we've installed, and I'm just going to represent the rest of the molecule as a phenyl group. Okay, and then from that point on, getting to this product is just a matter of using acid, water, and heat to do the ester hydrolysis, decarboxylation, and tautomerization. Once you've been through it a couple of times, you start to see it. Look for that methyl ketone that's alpha alkylated. And you need to go through this enough times that it starts to become a little bit more straightforward, a little bit easier. And once you see it, that's really all there is to it. Questions? Yeah. Well, you do need to know the mechanism because we went through that last time. We did go through that mechanism last time. I'm not drawing it out for you, but yeah. Yes?
So we lose the carboxyl plus
That's right. You lose CO2 and you also lose the ethyl group as ethanol. That happens in this step that is really hydrolysis of the ester, decarboxylation, and tautomerization. So yeah, the blue stuff goes away. All right, what else? Yeah?
Do you ever have concerns that you'll accidentally add like two of the same constituents or receptors?
Do you ever have concerns that you'll add two of the same group? No, and that's the beauty of this synthesis, and it's all controlled by the fact that these alpha protons are more acidic than ethanol, so that the ethoxide base removes it 100%, you make 100% enolate. At that point, once you've made the enolate, there's no more base present. So you add the second alkyl group, and at this stage, again, there's no base present to do the deprotonating. Yeah. So it tends to work pretty well. One other point that we could make is that though you can make alpha-alpha dialkylated methyl ketones directly via this method, you can't directly make alpha-alpha-alpha trialkylated methyl ketones. At this point, we sound like we're starting to found a fraternity or a sorority. This is an alpha carbon. It's got 3 alkyl groups on it. You can't make that directly from the acetoacetic ester synthesis. And I'll show you why. It's not as complicated as you think. There's a problem in your text that deals with this. And I know that anytime you're asked, why can't I do that? You wonder whether there's something weird and mysterious in the past or you're just not allowed to. No, the answer is it just doesn't work. And I'll show you why. And the reason really has to do with the fact that your I need a little bit more space. Acetoacetic ester starting material only has 2 alpha protons to be removed, okay? Here's the 2 alpha protons, and here's the blue alpha carbon. And while it is true that I could do sodium ethoxide followed by a methyl group with a leaving group on it to make the monoalkylated beta keto ester, and then I could do a second round to install a second methyl group. All of that works great and should be pretty straightforward to you. Once I install the 2 alkyl groups on the alpha carbon, at that stage, I am done. There is no additional proton that can be removed. So I can't make the enolate to install the 3rd alkyl group. The best I could do is at that stage hydrolyze the ester, decarboxylate, and tautomerize. That's going to, in the tautomerization step, put a proton back on the alpha carbon. But at that stage, the ester's gone, and so this proton isn't especially acidic anymore. If I wanted to install a 3rd alkyl group, I could try it, but I would be dealing with all of the problems that conventional thermodynamic enolate alkylation have. So and someone asked me last hour, well, couldn't I just take this, deprotonate that with a strong base like LDA? And the answer is no, because LDA go on the other side. Okay, well, couldn't I just use sodium ethoxide to make a very small amount of that and then add the 3rd methyl group? Yeah, if it works, because you're worried about the competing SN2 reaction. So basically, I can't make this triply alkylated methyl ketone directly from the acetoacetic ester synthesis. I would have to do something else to that alpha-alpha dialkylated molecule. Okay, sort of a minor point. It shows up in a question, but you know, the question is, why can't you make this? This is the reason why. All right. Now I want to spend a little bit of time talking about biological decarboxylation. This doesn't fit neatly into the chapter because it doesn't really involve alkylation, but it is an example of decarboxylation, which we have just learned about in the acetoacetic ester synthesis. So it's a good time to talk about it, and it's something that'll be easier for you when you get to biochemistry. So some of you may have heard about the amino acid histidine before. If you haven't, that's fine. In about a month, you're going to memorize the amino acids, which I know you're looking forward to. It's okay because you're going to thank me so much when you get to 481 in biochemistry, and suddenly the first month of 481 is going to seem easy to you. And you need that kind of a win in your life right now. You need to go to a chemistry class and feel like this is easy, all right? So today is not that day, but that day is coming, and we'll get there. All right, so this is the amino acid histidine. It's got this carboxylic acid group on it. Nature uses an enzyme called a decarboxylase to remove CO2. There is a cofactor that's involved in this. It's called PLP. You've met PLP before. We used it to do transaminase reactions where we're moving amino groups around by interchanging various imines. PLP will have a similar but slightly different role in this decarboxylation reaction. But when the reaction is done, what you're left with is everything else that was in the molecule to begin with, except no CO2 group. There used to be a proton there on the alpha carbon. Now there are 2 protons on what used to be the alpha carbon, but CO2 is gone. And this is called histamine. That's the one you've probably heard of, histamine. Maybe if in springtime or around animals you get an itchy nose and runny eyes and runny nose, you've taken antihistamines before, and they suppress the action of histamine. Sometimes you got to be careful. Sometimes they make you drowsy. I once had a near out-of-body experience while playing the organ in sacrament meeting after I had taken 2 Benadryl. So yeah, it was kind of focus on the page, and go ahead.
Something happens to the double bond on the ring.
Yeah, sorry about that. There should be a double bond there. My bad. Okay, it turns out this same reaction process is used to convert some other similar amino acids to some other signaling molecules that you may be aware of. For example, here is the amino acid tyrosine. You'll learn about it later. It has this stereochemistry. It's kind of like histidine, only you've got a benzene ring and a para-hydroxy group here. This is called tyrosine. The amino acids have a 1-letter code, and tyrosines is Y because we use T for something else. So Y is for tyrosine. You will use the same set of reaction conditions, but a different enzyme, using PLP as a cofactor, and that will leave everything about the molecule. Oops, sorry, I gotta rewind and delete because we weren't quite ready for that. It turns out that before biology does the decarboxylation reaction, it does an oxidation reaction that you don't need to worry about. That oxidation reaction installs a second OH group on the tyrosine benzene ring. So now this amino acid is no longer tyrosine. It's got 2 OH groups on it. This one doesn't get incorporated into proteins, but you may have heard of it before. It's called L-DOPA. And you can do the decarboxylation reaction mediated by PLP. And what's left behind when you do that is still the benzene ring with the 2 OHs. But again, the CO2 group is gone, and in its place, you've got a proton on what used to be the alpha carbon. And this is called dopamine, which is a neurotransmitter, and you hear about it a lot lately. Most recently, I've heard about dopamine scrolling, where I think people hypothesize that it takes advantage of our treasure hunting instincts to constantly be scrolling and looking for a hit of dopamine that tells us we found something interesting. Some of you may identify with that. Other people call it doom scrolling. Yeah. Hopefully you get more dopamine than doom, but anyway, yeah, as we ponder, as Amber and I ponder as parents, anytime our kids ask us to do something and it's going to involve some effort on our part and we are lazy because we are in our 40s and we are tired, we are not, my wife is not lazy. I try not to be lazy, but sometimes I'm lazy. We are, however, tired a lot of the time. Anytime we're tired, we get a request, we think to ourselves, okay, is sitting on their bed scrolling, looking at a screen superior? No, it is not. Okay, we got to do it. So anyway, the other neurotransmitter that we'll talk about today is related. It's like tyrosine. It's going to have the same carboxylic acid. It's going to have the same ammonium, the same hydrogen, the same beta carbon. Only what's here is a little bit different, and I'm afraid I'm going to get this wrong. So, what the heck? I think this is right. Yep, that's right. So this amino acid is called tryptophan. You've heard that one before, probably because people are explaining to you why you feel sleepy after you eat turkey, and somebody once had some idea that it was the tryptophan in the turkey that helps make you feel sleepy. I don't know how much science there is behind that because I'm not a neuroscientist, so somebody Google it and look it up, but this is the amino acid tryptophan. It's found in proteins. Its one-letter code is W, which doesn't make any sense, but we can't use the T or the Y because we've already used them for other things. So anyway, I remember it by pronouncing tryptophan twiptophan, and that is useful. So anyway, biology will also install an OH group on tryptophan at this position. And then it will do the decarboxylation reaction, again using a different enzyme, but basically the same reaction mechanism, which we will talk about. And the product of that is this guy here, which you've probably heard about. This one is called serotonin. Right, okay. So these are all neurotransmitters or signaling molecules, and they're all prepared via the same type of decarboxylation reaction, which we will go into. Before we do that, as just a little aside, some of you have heard about serotonin in terms of medications that are designed to elevate serotonin levels in your brain, and those are called SSRIs, or selective serotonin reuptake inhibitors. You heard of those before? Sure. I'm not a neuroscientist, so I don't necessarily know a lot of the neuroscience, but at least there was a hypothesis that some of the symptoms of depression, anxiety, even perhaps some symptoms of ADHD could be attributed to levels of serotonin not being what they should be in the space between your synapses. At least the way I understand, which is not very well, the neuroscience is the neurotransmitter's released, the signal is sent, but then you need to take up the neurotransmitter again inside the neuron to make the signal go away. And there are receptors that do that, and the SSRIs inhibit that process, allowing serotonin to persist longer in the brain. And it's thought that that can help with some of the symptoms of some of these mental health situations. So here is a molecule that is an SSRI. It's called sertraline. Trade name, at least when it was initially disclosed, was Zoloft. And I actually, now this is personal confession, although sometimes when you share things about your life, it's awkward. Other times when you share things about your life, it helps other people feel like, oh, okay, well, I have similar experience. So I've actually been on SSRIs before, including sertraline. I'm actually on one now, and its side effects are kind of interesting. So I don't know, I was on it before for a long time, and if you've ever taken meds for mental health, you get feeling better, and then you think you don't need them anymore. And so about a year or so ago, I was feeling great and sort of stopped taking it. And felt mostly good, but there were some symptoms that started to creep back in. So I met with my doctor, and he was like, "Okay, we should get you started on again." Halfway through that year, where I was off the meds, I kind of thought maybe I should start again, and I started again at my previous dose, which was like 100 milligrams. And apparently that was a dumb thing to do because I took it, and one of the side effects if you take a large dose is you wake up in the middle of the night at 2 a.m. totally awake and you can't go back to sleep. So I got really angry and decided not to take the meds, and the symptoms got worse. Anyway, so I went in and told my doctor about this. He's like, "Okay, dummy, let's start you out at 25. He didn't actually, 25 milligrams. He didn't actually say dummy. He knows I'm an OChem professor. He hated OChem, so if that gives you hope, that's good. Anyway, but even on the 25 milligram dose that I just started on about a week ago, it didn't wake me up in the middle of the night, but there's some weird symptoms. I don't know if any of you have experienced these before. There's a little bit of dizziness when you first go on one of these, like you start, when I turn my head a little bit or move my eyes rapidly, it's not so bad, but I've noticed it before. The other bizarre one is I wake up in the morning, start chewing my cereal or eating crackers at lunch, because I like cheese and crackers, and my jaw hurts. I'm like, what the heck? My jaw is tired, and it's one of the known side effects of this drug is it tightens your jaw muscles, and so I don't know if it's because I'm smiling so much because I'm suddenly happier or what, but anyway, all these things sort of get better over time. That's been my experience. Anyway, and if you have my mental health issues are not severe. I'm not even officially diagnosed by anybody with depression and anxiety, but I've had symptoms of things, and it helps me manage them. So if you need help with I encourage you to talk to trained professionals and don't necessarily take the advice of an OChem professor who doesn't know anything about medicine. I want to say just a little bit back to science about this molecule sertraline. If you've ever been prescribed it before, you'll notice that it comes as sertraline HCl. Now, after having taken Gen Chem and known that HCl is a strong acid, maybe that has given you some pause. I thought, isn't it bad to put acid in your medicine? Is that a bad thing? It turns out what they're actually doing is they are adding HCl, but the sertraline itself is a base. That nitrogen is basic. And so all they're doing is they're protonating the amine to form the ammonium salt. So this is the positively charged ammonium salt, and then Cl minus is the counter ion. And nobody wants to draw that on the label, so they just write it as sertraline HCl. So in chemistry, we call the neutral form of sertraline, because it's an amine and it's a base, we call that the free base, and then we call this the hydrochloride salt. And it turns out the hydrochloride salt is often more soluble and easier to formulate than the free base. The amine form is sometimes more soluble in organic solvent than it is in aqueous solvent. Of course, if you want to take a medication orally, it's helpful if you can swallow it and it dissolves in your guts and then gets absorbed through the epithelial cells. So the HCl salt happens to be easier to formulate and more soluble, so that's why it's HCl. If you're interested in United States federal government drug enforcement policy, there's another interesting free-base HCl salt story you could look up about cocaine. The powdered version of cocaine is the HCl salt. The free-base version is crack. It's less soluble. You have to heat it up to melt it, and you can't snort it because it's not in powdered form. I don't speak by personal experience, just by what I have read. But interestingly, And I won't comment on this in terms of opinion, but the penalties for consuming and trafficking the free base were much more severe than the penalties for consuming and trafficking the HCl salt, even though they did the same thing. And anyway, it's an interesting story to read, and we'll leave it at that. But that's our foray into free bases, amines, mental health medication, and we haven't even talked about the decarboxylation stuff yet. So, is it okay if we do that? Can we do that now? I'm thirsty. Too much talking. Okay, so let's show you how this works. We'll do this with just a generic amino acid where we won't draw the side chain. That'll make our drawings just a little bit easier. Here's the ammonium, and then here is the R group, the side chain. And there's a hydrogen there. Good. All right, so all of these decarboxylase enzymes use PLP as a cofactor. You've seen it before. Here it is again. You've got a benzene ring with a nitrogen where the nitrogen has a positive formal charge. Immediately to the right, a methyl group. Immediately to the right of that, a hydroxyl group. Up here, a CH2 phosphoester, and then the business end of the molecule, which is this aldehyde, and that's PLP. The first step of the mechanism of the reaction is just imine formation, which I'm not going to attempt to draw for you. I trust that you know what that is or know where you can go to review imine formation. First, a base would deprotonate the ammonium ion to give you the amine, then the amine would attack the carbonyl carbon, and so on. That's a nucleophilic addition reaction. What I'll do instead is we'll just draw the imine and assume that you know how to get there. If you don't, you can go to chapter 14 and it will give you a detailed step-by-step way to get from the aldehyde and the amino group to the imine. So now the nitrogen of our amino acid is tied up in an imine with the PLP aldehyde. I'm going to use the color blue to indicate the alpha carbon. Here is the side chain, and here is the hydrogen. There's the alpha carbon, and here's the carboxylic acid. All right, we'll call this the PLP imine. Now we're ready for decarboxylation. And before I show that to you, I'm going to remind you of something I told you last time, which is how beta keto acids can decarboxylate. And I'll focus on the basic conditions where you're dealing with the carboxylate group. Recall that I told you that lone pairs on the carbonyl oxygen can kick down and kick off the carbon alpha carbon pi bond as a lone pair onto the alpha carbon. And the reason that can happen is because the lone pair on that alpha carbon is stabilized by resonance with the carbonyl that's on the blue beta carbon. So here's the blue CO2 that comes off, and then here is that resonance stabilized enolate. This is the other resonance structure, okay? Notice the structural pattern. Carboxylate and then beta to it, you have a pi bond, such that if this bond here between carbonyl carbon and alpha carbon broke, the lone pairs would be resonance stabilized. Now take a look at the PLP imine. Here is our CO2 group. Here is the alpha carbon. Here is the beta position. Now it is not a carbon, but it is involved in a pi bond. Do you see that structural similarity? And the thing it's bonded to is not an oxygen, but if you imagine lone pairs on this carbonyl oxygen kicking down to form a pi bond and making CO2, then the electrons in the bond between that carbonyl carbon and the alpha carbon would have to go here. And you can see that if they did, they're going to be adjacent to this pi bond where they'll be resonance stabilized. So I'm going to draw that intermediate, And I'm going to show you how that resonance stabilized intermediate is much more delocalized, even more stable than the enolate intermediate I showed you above. So here's the CO2 that goes away as a byproduct of the reaction. I'm missing a positive formal charge on that nitrogen, sorry. And then here is the resulting, the thing that's left after we do the decarboxylation reaction. All right, there's the nitrogen. There's the alpha carbon. Still on it are the R group and the hydrogen, but what we're left with is a lone pair. Now, I've shown you this decarboxylation mechanism differently than your text shows it, but what I have showed you is exactly equivalent to what's in your text. And I'll show you how that's true now. First, in pink is the lone pair. Do you see how that lone pair is adjacent to this pi bond? So it ought to be possible to take the lone pair here, make a pi bond between alpha and nitrogen, then break this pi bond and move the lone pair there. That would be one resonance structure. And I'm not going to draw that, but imagine in your mind a pi bond here and a lone pair here. Then that lone pair itself could hop over to form a pi bond here, and then we could move this pi bond as a lone pair onto that atom. And so we could continue around the ring. Every other atom is a place where that lone pair can be. So it's much more highly delocalized than the enolate that we dealt with above. In the enolate above, the lone pair could only ever be on 2 places. Here it can be on 5. So it's much more delocalized, much more stabilized, a much better leaving group, and that's why this is a much more favorable decarboxylation reaction. In fact, if you want, I will show you using arrows how to convert one of these resonance structures into another, and these are the very same arrows that your text uses in its mechanism. Because instead of showing the lone pairs, instead of showing the bond between carbon and alpha carbon, move on to the alpha carbon, your text jumps directly to the resonance structure I'm going to show you. So we could move these lone pairs here to form a pi, this lone pair here to form a pi bond, move this one here, move this one here, and then finally these come out onto the nitrogen. When we do that, we obtain this resonance structure. And remember what resonance means. It's not a different molecule, and the electrons are not hopping back and forth. We just mean that the lone pairs are delocalized. The lone pair is delocalized on all of the places that I showed you. Your text likes this resonance structure because it is neutral. It avoids having a negatively charged alpha carbon and a positive formal charge on the ring nitrogen of PLP. And it looks like I got that part wrong. There we go. All right. So hopefully you can see how these two are resonance structures of each other. Here's the lone pair on that nitrogen. I'm going to continue to use the pink highlighting to indicate the atoms that share that lone pair. All right? So, all the rest of that PLP molecule that you were thinking about before, what's that for? It's designed to delocalize the electrons on the alpha carbon. Okay, what happens next is pretty easy, and it's actually most convenient to show what's happening next from this resonance structure. So to avoid having to draw too many arrows, I'm simply going to draw the mechanism from this resonance structure. We'll keep the pink highlights because they demonstrate that that lone pair is delocalized. We're going to protonate on that blue alpha carbon. Either a group from the enzyme or solvent does this. At that stage, we will have the following molecule. Again, it's a pain to draw all of PLP, but you really need it all to see how the reaction works. Now, if you compare where we were to where we are now and where we need to get, I'm scrolling upward briefly to show you some of these neurotransmitters like histamine, where the CO2 is gone and in its place you have a proton. We are almost there in our mechanism. All that's left is now to hydrolyze the imine. And I won't show you that mechanism because you know it. You've seen it before, and if you need to review it, it's in chapter 14. That will regenerate the PLP aldehyde, and importantly, it releases the amino group. It releases your now neurotransmitter, which has the amine and the side chain still, but is the carboxylate is missing, and in its place is a proton. Okay, questions about that process? Yeah.
So is the molecule on the upper right the same as the molecule on the
Upper,
on the bottom left? Like,
you're asking about this and this. Yes, it is. I just redrew it because I didn't have space. All right, what else? Okay, well, in the last 10 minutes, we need to take a moment and talk about a reaction that actually was earlier in the chapter, but is easier, and so I didn't want to spend as much time on it. And this is alpha halogenation of carbonyls. So in this reaction, we're going to use an enol as a nucleophile. It's related to using an enolate. The enol is the conjugate acid of an enolate, and we're going to use Br2 as the electrophile. You've used Br2 as an electrophile before in 352, in which you had the pi bond of an alkene attack the antibonding Br2 sigma star antibonding orbital to create a new sigma bond with the less substituted carbon and a positive charge on the more substituted carbon, and then Br minus was the leaving group. You saw that in 351. What we're going to do today with enols is going to be somewhat similar to that. The conditions are we start with a ketone, and we're using Br2, and we're using acetic acid, probably as a solvent and as an acid catalyst. And the effect of that reaction is to make a new bond between the alpha carbon of the ketone and bromine. And that is what is called an alpha halo ketone. And alpha halo ketones are very synthetically useful. So I'm going to go through this mechanism pretty quickly, and then we'll spend most of the rest of our time talking about what you can do synthetically with alpha halo ketones. So what likely happens first is tautomerization of the ketone to the enol form. You protonate the carbonyl carbon. This should be review because you've done tautomerization before. You get to the oxonium ion, and then you can have your base the conjugate base of your acid, remove a proton from the oxonium ion to generate the enol tautomer of your ketone. So that's keto form to enol form. Then you can draw the next step in a couple of different ways, but an easy way is to have the pi bond attack Br2 to create a new sigma bond between the alpha carbon and Br. We're doing that so that the positive charge on the carbonyl carbon, the positive charge can be on what used to be the carbonyl carbon where it is stabilized by resonance with lone pairs on the carbonyl oxygen. Oops, that didn't work. If you want an alternative for how to draw this mechanism, you could start from this alternative resonance structure of the enolate. I'm sorry, this alternative resonance structure of the enol. And that would get you to exactly the same place. At that stage, getting to our product just involves a base removing the proton from the oxonium ion. In your text, that base is Br minus, and that will get you to the indicated product, which is this. Okay. I am sorry that that drawing is messy, but my hand is tired because I've been doing this since 9 a.m. So here we go. I bet your hands are tired too. Your hand ever ache after getting out of OChem class? Yeah. All right. Questions about the mechanism?
What was the last step again?
Last step is deprotonation of the oxonium ion to get the alpha halo carbonyl. You can show that deprotonation either in the way I've shown you below or this way. Both of those are fine. They are fully equivalent. Okay, now I want to spend just the last few minutes telling you what you can do with alpha halo ketones. So imagine starting with this carbonyl group and doing the alpha halogenation. And imagine installing the Br on the alpha carbon. Think of what you can do with this. With alkyl halides, you can do nucleophilic substitution reactions in which you take a nucleophile that's good at doing SN2 and you do that expected SN2 reaction. So a structural pattern you're looking at to give you a clue that you needed to use an alpha halo ketone as a starting material was look for an alpha carbon where what is possibly a nucleophile, where what could have been a nucleophile is attached to that alpha carbon. Let me just give you a brief example of that and show you what the nucleophile is, and then I will leave it to you to sort of think through the mechanism. The nucleophile in the previous step would have been this thiolate. Okay? What about elimination steps? If I have this alpha halo carbonyl, I could do an E2 reaction, and that would have a base remove the proton on this carbon to create a pi bond here and the leaving group left. That's an E2 reaction, and importantly, that generates this alpha beta unsaturated carbonyl compound, which we have learned already from chapter 13 we can do other things with, right? The base that you might consider using for this reaction, if you were in 351, you probably would have used tert butoxide, and that's okay. However, your text presents an alternative that I don't need you to memorize, but I at least need you to recognize. I don't know why your text does this other than these conditions actually work, and the text author is a synthetic chemist and cares about what actually works, not just what you imagine would work. So the conditions that your text will often use for this elimination reaction are to use lithium carbonate. Carbonate is a base that looks like this, and the negatively charged oxygen is the one that acts as the base. And then as an additive, you use lithium bromide, which is just a salt. So you have a base and then a related additive. Your text provides no explanation for why you need both of these things. I don't know whether it's empirical, if they just tried it until it worked or not. I can't tell you why they're adding lithium bromide, but you will need to recognize those. In order to do the problems in your text, you'll need to recognize those as a base that will do the E2 reaction. Okay, I maybe have a bit more to say about that next time. I'll see you on Monday when we'll move on to chapter 18. Yep, see ya.